Hello, welcome to my channel Chemical Engineering Knowledge. In the previous lectures we have discussed about the mass transfer theories, the turbulent theories, the penetration theory, the surface renewal theory, the boundary layer theory. Then we discussed the relation between the average and local heat and mass transfer coefficients. In this lecture we will discuss the momentum, heat and mass transfer analogies. So momentum, heat and mass transfer analogies. So in the transport phenomena we are discussing three important phenomena. As we know that in transport phenomena we are discussing three important phenomena. One is momentum transport, the second one is the energy transport or heat transport, and the third one is mass transfer or mass transport. We are discussing these three phenomena on molecular level, and on large scale. So in transport phenomena we are discussing three important phenomena. One is the momentum transport, the second is energy transport, the third is mass transport. Now what is the momentum transport? In momentum transport we are discussing the transfer of mass and velocity. We are discussing the transport of velocity. We are discussing transfer of mass and velocity, which is momentum. So in momentum transport we are discussing transport of mass and velocity. The famous law for momentum transport is the Newton law of viscosity. The Newton law of viscosity is tau xy minus mu into dvx by dy. Suppose we have a pipe in which some fluid is flowing. This is the fluid. On the surface there is no slip condition. Velocity increases and decreases, and it forms the parabolic like profile inside the pipe. This is the fluid. Here the no slip condition, velocity is 0 at the surface of the wall. Now this velocity is Vx. The velocity here is Vx, and suppose this is the y direction. So the Vx is changes in the y direction. Here velocity is 0, Vx is 0, here Vx is slightly increase, here further increase. The maximum velocity is in the center of the pipe, then decreases, and here is 0 again. So it means that Vx is a function of y, and Vx changes is in the y direction, and this is the viscosity of the fluid. This is the shear stress in the y direction. So the Vx changes in the y direction, and this is the viscosity of the fluid. This viscosity of the fluid can be obtained from the various correlation and tables and various correlations. So in momentum transport the velocity changes in the y direction. Similarly in the energy transport there is a temperature gradient. The temperature changes in the x or y or z direction. So in the energy transport the second important transport phenomena is the energy transport. What is the energy transport? In energy transport, we are discussing the change in temperature. We are discussing change of temperature. We are discussing change of temperature or change of energy. So the famous equation for the energy transport is the Fourier law of molecular diffusion. So for energy transport, the famous law is the Fourier law, and the Fourier's law shows us that the heat flux is equal to minus K into dT divided by dx. It means that this is the thermal conductivity, this is the temperature gradient. Suppose we have a thick material having thickness delta x. Some hard fluid is on the one side of the wall having temperature T1, on the other side temperature is T2. This is a cold fluid and this is the hot fluid. The temperature will decrease in the x direction because heat will transfer from the high temperature region to the low temperature region. So the temperature will decrease in the x direction, which is dt by dxo, and this is the thermal conductivity of the material. Of this material, the thermal conductivity can be brick or some wall or some other material. So this is the heat flux. So similarly, in the mass transfer, there is important law which is called the Fick's law of molecular diffusion. The Fick's law mass transfer. The third important transport phenomena is the mass transfer, which is the important transport phenomena. The mass transfer can be denoted by the Fick's law of molecular diffusion. So the Fick's law can be written as, mathematically it shows that the molar flux of component A is equal to minus diffusivity of component A in B into dCA by dZ. So this is the diffusivity of component A into the component B. Again, it is obtained from the correlation and tables and graphs. And this is the concentration gradient. This thermal conductivity can also be obtained from the various equation and correlation. So this is the concentration gradient for the transport phenomena. So in transport phenomena, we are discussing three important phenomena. One is the momentum transport, the second is the energy transport, and the third is the mass transport. The mass transfer, which is the Fick's law, and the mathematical form is minus dAB dCA into dZ. Suppose we have two compartments. There is some wall between the two compartments. There is component A, gas A. Suppose this is gas A, here is gas B. Suppose if we open the wall, component A will transfer from the high concentration region to the low concentration region, and it will cover some distance, which is dz. So this is the concentration here is high, which is C1 suppose, and the concentration here is small, which is C2. So C1 minus C2 is change in the concentration, and this is dz is delta z, and dAB is the diffusivity. Suppose this is the component B and this is the component A. The component A is moving and it is the component B is coming to the component B, and it transfer through the component B. Suppose these are the component B and this is the component A. It is transferred through the component B. So this is show us the diffusivity of component A and component B. And simply suppose this is the component B and suppose this is the component A. The smallest component A. It is passing through the component B. So this component, this suppose component A, and these are the component B. They are the component B. So the dAB show us the transport of component A through the component B. So this is called the diffusivity of component A through the component B. Now, up to now we have discussed the three transport phenomena. The momentum transport. The momentum transport is denoted by the momentum flux, which was tau xy, minus mu into dvx by dy. This is the momentum flux. Momentum flux. The heat flux is denoted by q is equal to minus k dt by dx. This is the energy or heat flux. Heat is a form of energy, so this is the energy or the heat flux. Heat or energy flux. The third one is the mass flux or molar flux, which is minus dAB dCA by d ZR mass or molar flux. Molar flux or mass flux by relation, which is mole is equal to mass by molecular mass. So mass by molecular mass. If we multiply here by molecular weight of component A, we will get the mass flux. So now, up to now we have discussed the three important transport phenomena: the momentum transport, the energy transport, and the mass transport. The momentum transport equation can also be written as minus mu into dvx by dy. Now suppose if we multiply vx by density of the fluid and divide the viscosity by density of the fluid, we know that we will get this relation, which is minus kinematic viscosity into density into velocity divided by dy. Now density divided by viscosity is nothing but is the kinematic viscosity of the fluid, which is the momentum diffusivity. It shows the momentum diffusivity. Suppose this is equation number 1. Now from equation number 2, from equation B, which is the heat flux, which is nothing but minus k dt by dx. This is the temperature. If we divide k divided by, if we divide k by rho density of the material and specific heat or heat capacity of the material and multiply by rho and Cp, we will get another relation, which is minus thermal diffusivity. K divided by rho Cp is nothing but thermal diffusivity. If you don't know thermal diffusivity, watch my lecture related to the thermal diffusivity. Now we can further d by dx into rho Cp into T. Suppose this is equation number 2. This is equation number 1. This is equation number 2. Now the molar flux is minus dAB dCA by d Z. This is equation number 3. If we see to equation 1, 2 and 3, this shows the momentum diffusivity, this shows the heat diffusivity, and this shows the mass diffusivity. And these equation 2 can be obtained from equation 1 by analogy. Similarly, equation 3 can be obtained from equation 2 by analogies. And the unit of all these diffusivity, the unit of momentum diffusivity, the unit of heat diffusivity, the unit of mass diffusivity is same. And the unit of these all three diffusivity is square meter per second. So the unit of this momentum diffusivity is square meter per second, the unit of thermal diffusivity is square meter per second, the unit of mass diffusivity is square meter per second. So the unit of all these three quantities is same, which is square meter per second. Now these equation 1, 2 and 3 are for the laminar flow. Now if someone is interested to increase the transport of momentum, energy and mass, then he will use the turbulent flow. In the turbulent flow, the momentum flux is increased. So similarly, in the turbulent flow, the momentum, heat and mass fluxes are increased. So in turbulent flow, the transport of momentum, energy and mass are increased. And this equation 1, 2 and 3 are on the basis of and are on the molecular level. So on molecular level we can study momentum flux using the Newton law of viscosity. Similarly on molecular level we can study the heat flux by using the Fourier law of heat conduction. Similarly on molecular level we can study the mass flux or molar flux by using the Fick's law of molecular diffusion. Similarly for the turbulent flow, equation 1 can be written as tau xy minus this is the kinematic viscosity plus E into V diffusivity for momentum into dVx into rho divided by dy. So this diffusivity is for the turbulent flow and it is very high. It is 100 times larger than this molecular term. This is the molecular term which is on molecular level, and this is for the turbulent flow. For the turbulent flow these two terms are combined. So this is for the turbulent flow, the momentum flux is denoted by this equation, suppose equation M. Similarly for the turbulent flow, the heat flux is denoted by minus thermal diffusivity for heat, diffusivity for energy or heat, into rho Cp into temperature and divided by dx. Suppose equation N is for the turbulent flow. The heat flux in turbulent flow is denoted by equation N. The heat flux in the momentum flux in the turbulent flow is denoted by equation M. Similarly, the mass flux in turbulent flow is denoted by dAb into the diffusivity for mass into dCA by dZ. This is equation. Suppose equation number O. So equation O is to show us the combined molecular and convective mass flux. So the equation O is for the turbulent flow. If someone is interested to study the transport of mass in the turbulent flow, then equation O will be used. This is show us the molecular term, and the combined term is for the combined mass flux. So this two also shows the combined heat flux. This two term also show us the combined momentum flux. So for the turbulent flow, equation M, N and O are used. And turbulent flow, the momentum flux, the energy flux and the mass flux are increased. Turbulent flow increases all these three transport phenomena many times. That means that it can increase the mass transport, energy transport and momentum transport 100 times as compared to the molecular transport. So this is all about the momentum, energy and mass transport analogies. Thanks. If you are new to the channel, please like and subscribe.